Mic test 1, 2, 3. Hello, hello, hello. Am I audible? 5, 4, 3, 2, 1.
தேவையில்லாம இன்னொரு லேப்டாப் இல்ல வந்தது இல்ல வந்தது இன்னும் வந்து சோசியத்து வந்து அது அவரு என்ன பிளான் பண்ணாங்கன்னு தெரியல நாளைக்கு ரிட்டர்ன் இருக்கு இல்லையா அதனால தான் அட்லீஸ்ட் வரிசையா வச்சு அது வரிசையில கம்ப்யூட்டர் சேர்த்துருக்காரு இன்னைக்கு வந்து இருக்கு பட் வந்து ஒன்லி நினைக்கிறேன் அது வந்து ரிட்டர்ன் கிடையாது நாளைக்கு தான் வாங்க வந்து ஏதாவது சாப்பிட்டு வரலாம்
நீங்க ஸ்கிரீன் ஷேர் பண்ணும்போது அதை மட்டும் பெருசா வச்சுக்கோங்க. எதுவுமே பண்ணாதீங்க. ஸ்கிரீன் ஷேர் இப்ப பண்ணீங்கன்னா ஏன் எனக்கு இன்னும் வரல பிபிடி போடுங்க தனியா போட்டு இதுல ஷேர் பண்ணுங்க பெக்ஸி அப்படியே விட்டுருங்க ஷேர் போட்டு அந்த பிபி என்ட்ரி ஸ்கிரீனே கொடுங்க எப்பயுமே என்ட்ரி ஸ்கிரீன் ஷேர் பிபிடி மட்டும் கொடுக்குறேன். ஓகே எனக்கு வந்துருச்சு இது இப்படியே இருக்கட்டும் வியூவு கரெக்டா நீங்க எதுவுமே டச் பண்ண இன்னைக்கு இங்க ஓபிஎஸ்ல போயிட்டு இருக்கு.
overview PPT இல்ல overview டெஸ்க்டாப்ல பிபிசி வந்து இதுல என் லேப்ல கூடாது இப்போ உங்களுக்கு பென்ட்ரைவ்ல வேணுமா உங்களுக்கு பென்ட்ரைவ் இருக்கா எனவே செஷன் மதியம் தான் 3 o'clock இப்பவே வேணாம் உங்களுக்கு ஓகே நான் லஞ்ச் டைம்ல கொடுத்துறேன் Can you put that with it?
The green color, maroon color PPT எங்க இருக்கு சார்?
இதுல அந்த மேல போட்டுக்க பாருங்க சென்சார்ஸ் அப்படின்னு சொல்லி
அந்த போட்டோ தான். Here from here.
கீழே பாருங்க
No, this timing is important because the botany is shifted.
Oh, okay.
Okay. Madam, can you ask Prabha to ask all the technical session people to come here?
It's a magnet. You just
No, no magnet, nothing. Simply mechanical system we have to.
no. It will be secret.
Do you have the details about the professor to give introduction?
No introduction, sir.
About the professor,
Which professor?
or IIT professor?
He is presenting
Yeah,
now.
presenting.
Bobby George?
Not professor.
I'll,
Christian, Christian.
I'll make it ready.
சார் சார் இப்போ ப்ரெசென்ட் பண்றவங்களோட பேர்
We made it, you know.
No, sir. You have, sir? Kindly forward to me.
We should have.
No, for this people who are not giving any introduction as.
Let's say a gift professor from IIT.
That is there. That is there. Professor Krishnan from IIT Madras who will take us through innovation of.
And he is the chairman of so many things and all that.
And I have already written Professor Krishnan, head Center for Non-Destructive Evaluation IIT Madras.
That's all, sir.
Yes, yes.
That had some good.
Not possible to take. Already we are late by half an hour. Yes, sir.
சார் கிருஷ்ணன் சார் கிட்ட போர்டு அங்கே வச்சுட்டேன்
Sir, sir, sir.
Oh, speaking English.
Yes, yes, sir. Yes, yes, sir. Yes, sir. Yes, sir. Tell me, sir.
So many.
We will. He will receive. Good morning, everyone. I hope you had a refreshing break. As we move on into the core of today's workshop, we have an exciting lineup of technical talks by esteemed experts in the field of oceanographic sensors and systems. The sessions will provide valuable insight into the latest advancement in indigenous developments and future prospects of ocean sensor technology. Without further ado, let's begin with our first session. The speaker for the first session is Mr. M. Sankar, Scientist G, Marine Sensor System, NIoT. And the title of the presentation is Sensors and Systems for Oceanographic Application and Need for Indigenization. Sankar sir is a distinguished scientist at NIoT specializing in marine sensor systems. His talk will highlight the crucial role of indigenization in oceanographic sensor, emphasizing the need for self-reliance in this domain. Let us welcome him. Over to you, sir.
Thank you, Kishore.
சார் எதுவுமே இங்க பாப்பா இங்க வெளியில போய்
அது வந்து இப்பெல்லாம் வந்து in between countries ஆயிடுச்சு. அதனால வந்து control
புரியுது
அது control வந்தாதான் என்னால என்ன பண்ண முடியும்.
புரியுது
அதனால
I request students to kindly grace the front seats. I request everyone to kindly grace the front seats. If they are still empty, we can go to the back seat. Please, there I could see. Please. Thank you very much. Now, I request Sankar sir to kindly go ahead with his presentation. Over to you, sir.
Very good morning to all of you, respected former group mates and respected professors from IIT Madras and scientists and engineers from national labs and distinguished speakers from various national labs. Very good morning to all of you once again. And my area of talk will be mainly about the mandate of the institute and the program that ocean observation system that we are that we operate and the importance of the sensors and system required for to operate and maintain this program, and also we have a technological groups to support this program for indigenization of sensor and systems. So these are the areas where I'll mainly cover. And secondly, I'll also talk about the area of technology where we have to concentrate to develop various sensors and systems to support this program. There is ocean network program.
start to present it.
And the institute, one of the main focus is to develop the reliable indigenous technologies to address the various engineering challenges that are related to harvesting of both living and non-living resources in the Indian exclusive economic zone. And we another main mandate is to protect the large coastal population who are vulnerable to ocean hazards by way of protecting the coast and also giving warning systems like cyclone, tsunami, and also protecting the environment, ocean environment. So in order to carry out this, we have to develop technologies for development of sensors and systems, and also the sensor carrying platform like underwater vehicles and marine instrumentation and so on. And moreover, this collection of ocean observation, oceanographic data that we collect, that will be useful for policy makers to take a decision regarding the marine resource management, conservation, and environmental protection. Okay, so this workshop actually, what mainly we the objective of the workshop is to involve private industries and national labs and for a joint collaboration to develop these technologies. So, as we all know that one institute may not have all the facilities to develop a technology. So we have facilities and expertise facilities that is spread over the country. So we have to identify the right people to develop these technologies. Second, yeah. So NIOT has got a group called Ocean Observation System. The mandate of this group is actually to operate, maintain, and moot buoy observation networks, and also maintain the related telecommunication facilities in the Indian seas. And this group actually has got a network of moot buoys in the Indian Ocean around Indian coast. This group also, in order to operation maintenance, they also work on to develop facility for calibration and maintenance of the sensors in-house. And so to support this group, actually we have a technical group. One is the Ocean Electronics Group. This group actually helps in indigenization of some deep ocean observing sensors. For instance, Argo and AUPD, Autonomous Underwater Profiling, Drifter, and so on. And one more group we have that is called Marine Sensor System. This group fully concentrates on development of underwater acoustic transducer and systems. And coming to this ocean observation system, this group actually has got various types of buoys. There is Omni buoy, Med buoy, and Tsunami buoys. And this buoy actually collect the institute data and disseminate to INCOIS, that is Indian National Center for Ocean Information System, and also to various stakeholders through global telecommunication system. We have about 20 numbers of buoys around the Indian coast. And we have different types of buoys. One is the meteorological buoys. It carries the sensors for meteorological data collection above water. And each buoy requires, each buoy has got around 12 CTD sensors for underwater underwater measurement, underwater parameters like conductivity, temperature, depth, salinity, and also we have acoustic Doppler current profiler for measuring the ocean current and direction of ocean current. And in addition to meteorological data above water, we have many sensors mounted in this buoy. So each buoy, the value of sensors that we install, that each buoy houses is about more than 3 crores, more than 3 crores. And it has got anemometer, heading compass, humidity and air temperature, barometer, rainfall sensor, and radiation sensor, long and short wave. And we have another buoy called Omni buoys. Actually, this buoy houses sensors for atmosphere as well as underwater, and even underwater below 500 depth, 500 meter, even up to the mooring point. So it has, in addition to meteorological data buoys, it has got all CTD sensors and CTD and EDCP, acoustic Doppler current profiler. And third one is Tsunami buoys. This buoy actually houses bottom pressure recorder, and that pressure measurement is transmitted to buoy through acoustic link. That is acoustic modem collects this information and transmits this data to show station through satellite. So this information can be immediately passed on to institute like inquiries for advanced warning. And another group we have is a marine sensor system. This group mainly focuses on design and development of indigenous acoustic transducer and systems. And earlier, we have successfully developed underwater acoustic transmitter of wide band and low frequency, and we got patent for this. And also, we have developed hydrophone array in the same order of frequency. And with this system, we have developed subbottom profiler where this system is designed for a shallow water application, and it houses the transmitter, hydrophone, all the electron hardware on the surface float, and we had deck unit for real-time observation of the picture that the sonar captures from the seabed. And we have demonstrated the successful working of the system, and it is capable of penetrating up to 3 meters. And we also have transfer no have a we also signed TLA tripartite license agreement with Bell for transfer of this technology recently. Thank you. And this is the specification of the subbottom profiler. The working frequency is 4 to 12 kilohertz, and it has got a 2x2 array of transmitter, and its TVR is 145 dB, and source level is 200 dB, and operating depth is 30 meter, and penetration is approximately 3 meter, and the towing speed is 2 to 3 knots. And this is the view of the seabed strata captured by our subbottom profiler. And one is the manually we have buried some steel items in the fishing orbit that we could capture with the help of our subbottom profiler. And also we have took our subbottom profiler across the channel, fishing orbit channel, and we could measure the width and the depth of the channel, and also we can see the depth of penetration in the mouth area. And another project we handle is the development of indigenous side scan sonar. We have just started, and this is a dual frequency, 100 kilohertz and 500 kilohertz. And this is the image we have got when we surveyed at shipwreckage of Chennai fishing or off Chennai port. And another successful product we have developed is underwater acoustic telephone. This actually we are developing for manned submersible. We have successfully demonstrated working of the system up to 500 meter off Bay of Bengal. And we are working further to enhance its working capability beyond 500 meter, that is 6,000 and beyond for manned submersible. Next. And we also help the industry, private industry, for design and fabrication of transducer. We have recently got one project for fabrication of transducer that is for underwater, that is for acoustic wake seeking and homing system of torpedo for Indian Navy. This transducer we designed, fabricated, and we have done complete acoustic characterization test and pressure test at NIOT. And we have handed over this to the firm for RC acceptance test.
So we have another 5 minutes.
Okay. And we have another group, that is Ocean Electronics Group. This group mainly focuses on development of deep ocean observation systems like ARGO and AUPD, Autonomous Underwater Profiler Drifter. And the main purpose of this system is to monitor the changes in the ocean parameters, and also it helps for a long-term prediction on increasing intensity of cyclones, storm surges, fishery stocks, and sea levels, etc. And we have given a table here, the list of items that this group has so far developed, and it is all the items are around TR level 6-7 stage. And I'll briefly explain about each product in the next slide. And this is actually a water sampler. We might have seen a Niskin water sampler, which we used to collect the water sample at required depth. In the conventional sampler is actually uses a go-devil messenger to collect water samples at required depth, that it requires manually dropping of the messenger. Whereas this water sampler, it has got an electronic system and a pressure sensor, and we can from deck we can remotely operate the solenoid valve to close the lid and collect the water at exact depth of immersion. And another product we have developed is this artificial intelligence powered fish biomass estimation for sustainable aquaculture. Actually, this product is developed for open sea fish aquaculture, and this actually helps for real-time data for optimized feeding and stock management, and also it main purpose is actually to estimate the volume and size of the fish that has grown in the cage. And we have we will require industry support to enhance its features, like including many other sensors along with this. Next. And this is the open sea fish cage. It's about 10-meter dia, and it can be immersed 10 meter below the water level, and this cage actually we have made indigenously. Locally it is made, and we have a scope to increase the size of the cage even beyond 10 meter, that is 20 to 30 meter, and also it may require change of the the type of net to match the various species of the fish. So industrial collaboration may require to improve and modify this fish cage system. Next. And one of the main sensors that we use for ocean observation is CTD. Usually we import this CTD sensor from Seabird Electronics, and so we have been developing these sensors with the collaboration of IIT and some other institute, and we have just compared the data that we have measured using the imported one and the locally made. There are some differences, so still some fine-tuning work is going on in the development of this product. Okay. And this is a low-cost CTD profiler, and this can be, it doesn't require no vessel to stop and then operate the winch and lower and get the CTD data. Here, this sensor, we can just throw into the ocean, and it can submerge up to the set depth, and once the set depth is reached, there will be a dead weight. The dead weight will be de-linked. Once it de-linked, it will again pop up, it will come to the surface. And during the transit, it will measure all the CTD data. And another product we have developed, it's under development, is EUPD, Autonomous Underwater Profiling Drifter. This is actually, once we deploy in the sea, it moves. It moves based on the direction of ocean current, direction of ocean current and speed, and it moves from surface to deep, maybe up to 4,000 meters it can travel. And during this movement, it can measure all the ocean parameters like conductivity, temperature, and pressure, density, salinity. All these parameters can be measured, and the battery, battery power, at present the battery power can support maximum 180 cycles. And once the AUPD comes to the surface, the data will be transferred to shore stations. And we have another product called Sea Profiler. This is actually, while ship is moving, from one point to another point, during the movement, we can collect the CTD data by connecting this to a hydrographic winch. And this profiling actually from surface to deep, the depth depends on the speed of the vessel and the and the speed of paying in payout of hydrograph winch. Based on that, we can get a profile of the CTD with this small CTD profiler. Okay, quickly finish. There are many sensors we have identified that requires for a development of all these products. I have just listed out these 1 to 7. These sensors are required for development of fish cage. It is CO2 sensors, chlorophyll sensor, dissolved oxygen sensor, arsenic sensor. All this required for development of fish cage, and also there are many other sensors like SST sensor and nitrogen dioxide and also we need development of hydrophone and transmitters for underwater acoustic communication and imaging. There are so many sensors that we have listed that requires indigenization. These are the sensors actually we use for a ocean observation system. We have given the complete details for the make, model, resolution, accuracy, and range, and type of sensors. And for acoustic rated area, we need industrial support for development of sensors like transmitter to hydrophone, and it requires industry support for fabrications. And so for our underwater acoustic telephone, we need a power amplifier development, and also a development of ADCP, acoustic Doppler current profiler. We need industry support to develop these products. And we have a facility at NAOT for to support the industry since the facility may not be available everywhere. So with some of the facilities we have in NAOT are, we have research vessels to take the product to see and test and validate the products. And also we have some facilities at lab, for instance, acoustic test facility, hyperbaric pressure test facility, environmental chamber, and shaker system for shock and vibrations. I have the pictures of the facility here, and this acoustic test facility is a 60-meter long and 9-meter wide and 7-meter deep, and we can measure the following parameters, that is the directivity, impedance, phase, conductance, susceptance, electrical power output, and receiving sensitivity, transmitting voltage response. All this we can measure in the tank. And this is it is a view of the hyperbaric test facility. This facility helps to test the product within the campus. It doesn't, so it eliminates taking the product to the sea and deploying at deeper water. So within the campus, we can see whether the product developed is capable of withstanding the external pressure, that is hydrostatic pressure. And this is a shock and vibration test facility. The tester developed the electronic device. We can subject to shock and vibration. And maybe the vibration may be a sine or random or shock. And it can be accelerated up to 100 G. And we have a corrosion testing chamber. This is to test the material capability to withstand the corrosion resistance in the under marine environment. So, and we have environmental chamber to test the product, its ability to withstand a temperature range between minus 45 to 180 degrees Celsius and relative humidity 10 to 98 RH. So why do we need this indigenization? So I have just listed out few points. One main thing is the cost of sensors imported for one buy is about rupees 2 crores, and the sensors are very expensive with a long procurement and repair lead time. These sensors often require recalibration at the OEM facility at specific interval determined by the manufacturer. The lead time for re-export and recalibrations are also lengthy. Therefore, efforts must focus on indigenization of these sensors and establishing a calibration facility that meets international standards. Thereby, we can achieve self-reliance by developing, producing sensors within a country and reducing dependence on foreign imports, boosting domestic industries, and creating employment opportunities. So this is possible since the government supports Make in India, and also this can be done by research-based collaboration and research-based approach we can develop within the country. Thank you all for your kind observations.
Thank you very much, sir. Our next talk is titled Innovation Ecosystem for Inspection and Monitoring at Center for Non-Destructive Evaluation at IIT Madras by Professor Krishnan B. Professor Krishnan Balasubramaniam is an institute professor at IIT Madras and heads the Center for Non-Destructive Evaluation. With his over 40 years of experience and expertise in NDE, his research spans ultrasonic structural health monitoring and material characterization. A recipient of multiple prestigious awards, including the Abdul Kalam National Technology Innovation Fellowship, he has incubated several startups. His work significantly impacts manufacturing, quality assurance, and advances diagnostics. He will be taking us through the innovation ecosystem at CNDE and its impact on oceanographic monitoring. His expertise in non-destructive evaluation brings a unique perspective to this field. Over to you, sir.
இதுன்னு சொல்லுங்க.
It's opening. Don't worry. Don't worry. Yeah, very good afternoon. So, first of all, let me thank Shankar, Director Balaji, and everybody for giving me an opportunity to be here. And it's a pleasure. While we wait for this to open,
Sir, I just copy it.
I better just leave it. You do what will, it will open if you wait. The patient will open. The impatient will not open. It's a big file. There you go. So anyway, thank you so much for giving the opportunity. I will be taking about 15 to 20 minutes. It's a very short time to give a quick overview of what we are doing, particularly in the field of non-destructive evaluation and testing. So let me see if I have control over, where is the mouse? Yeah. Can I have the mouse on this side? If you could also sort of turn it around. Yeah. Okay. So basically, NDT is something that you need because no material is manufactured perfectly. We live in an imperfect world. So no material is manufactured perfectly, no structure is manufactured perfectly. And even if you do a good job, you do not stay, the material don't stay, just the way human bodies do not stay the same way. So just like in human body, whether you are during manufacturing or during production or post-production, when it's being used, you need to make sure that everything is intact and all right. And that's why. And how do you do that? You do that very similar to what you do with medical. In medical, if I am not all right, I go get myself X-rayed, I get myself ultrasound, MRI. These are technologies that are used. We use identically the same technologies, right? We use that. And only difference is that we are probing inside material structures that are not living. And that's a major difference. But there's a much bigger difference. Unlike a human anatomy that has not changed in hundreds of years, unfortunately, in the materials world, in the engineering world, materials change every year. Components and design change every year. Problem statement changes every year. So by the time you are ready to, and you have solved a problem, the problem is shifted out. Okay? So this is a huge challenge that we have. The other big challenge that we have is the fact that if you just talk in terms of, say, a ship, okay, ship has thousands and thousands of welds, An example, and weld is one of the areas that we need to inspect very carefully. So the volume, if you take a railways, you're talking of 1 lakh kilometers of rails that I have to inspect every 3 months, right? Bridges, I don't have to keep going on this. So the volumes are very large, and in some cases, the conditions are not very good. Underwater conditions, like this is what you're familiar with, underwater conditions are not as good as doing it on the ground, right? So that's a big challenge that we also have to. And finally, it's a very cost sensitive market, so you got to do it cheaper. So what we do at IIT Madras is we do deep research in this field. So we look at how we can solve problems that are unsolved and how we can take the physics and the mathematics and the engineering and the technology to make things that we want to do better. And so we basically look at three major areas. One is non-destructive testing. How do I inspect materials during the various stages more efficiently, cheaper, faster? But we also look at, can I do health monitoring? Can I take my sensors and put it into structures and then monitor? Just the way, I don't know how many of you have seen this. You can put a patch and monitor your sugar on a continuous basis. Absolutely game changer, all right? I've used it. It's absolute game changer. The exactly same thing. You completely change the way you operate. Previously I used to take a blood sugar test every 3 months. Today, it tells me every minute how my blood is. In the minute I ate that cake, I know in 20 minutes that my sugar is going to go up by 40 or 50 points. Okay, so then I will say, wait a minute, should I have eaten the cake at all? So the exactly same thing can happen when you have continuous data, and that's structural health monitoring. And finally, we also look at measurements as different. So I'm going to give you some few examples and of each one of them. But before I get to that, we are also working on trying to push the envelope on technology. So we are from academics, so we also have to be very relevant to what's going to happen 5 years, 10 years down the road. So we are looking at 5 different areas where we are pushing the envelope, trying to make sure that we make the sensors more ubiquitous. We try to also look at pushing the level. You do underwater sonar and underwater imaging, right? Now, can I? One of the things that if any of you are involved in underwater sonar, you know that there is a limit to resolution. Okay. Now, can I improve the resolution? So today we are doing what is called lambda by 80. Okay, lambda by 2 being the classical limit. Today we are doing lambda by 80. Now, can it work for sonar? I do not know. We'll have to check it out. But it's working for imaging of objects. Okay. So if I can imagine, I can do lambda by 80 instead of lambda by 2. Your sonar resolutions improve like crazy. Similarly, we are looking at edge computing. Computers that actually at the sensor level will do the calculations that you normally do in a supercomputer. How do I get that done at the edge computing? So where AI plays a very big role. And finally, we're looking at swarm robotics. So imagine you have thousands of these inspectors going around and taking data. So these are areas that we are working on. And this is a part of my team. They're not the only team, but we have faculty from different departments working together. In fact, we do a little bit of work with the ocean department, but mostly materials, electrical, civil, and computer science also. Extremely collaborative. We work very closely with many universities across. These are only universities which we have ongoing or a recent, either student exchange programs or programs where we have joint PhD programs and so forth, or joint funding that goes across the world, and we are dependent heavily for our funding from the industry. Okay, so whether it is manufacturing, aerospace, defense, transportation, energy, we work very closely with the industry. And what that has done, and that's very important, because we work very close with industry, what that has done is that has allowed us to actually understand the problems, solved the problems, but more importantly, made sure that this problem that we have solved actually translates into a product, made in India product, made for just not India but the world. Okay, so we have 13 companies that we have started in the last 15 years. Okay, now just a small snapshot is these 13 companies are all located within the 20 kilometers from this place right here, or even closer to IIT, and they employ about 1,200 people. That is more than what IIT employs. Okay, so that is the ability we have created, and most importantly, we have a footprint that is just not India. So many of them have offices in US, offices in Singapore, offices in Middle East, offices in Australia, and they are serving the world. And every one of them technology, IP, all owned by these companies, and some of them with IIT Madras. Okay. So what is proven to us is that we can develop technology, and many of them are technology that are not available elsewhere. Okay. So that is the advantage that we have. So I'll just give a couple of snapshots. So one of the areas that we specialize in is robotics and automation for ensuring safety. All right. So whether it is on the left side, whether it's underwater, in fact, Planis Technologies is about 5 kilometers from here or less. Okay, in Pulidivakam. All right, and in fact, it has its roots to the ocean department and a little bit on NIOT also. A couple of these guys actually did internships here. All right, today they are probably not just India's largest shallow water inspection company, with bridges, dams, ports, all near the front. They go up maximum 100 meters deep. Okay, but they are one of the largest technology companies. Now, another example will be inspection of corrosion in offshore structures. A company called Dhwani Inspection Technologies, and similarly for high tall structures, this particular video on the right side, we're using drone-based inspection of the large storage tanks, was taken in 2016. Okay, so today it's become more commoditized, but we were pioneers in that. Similarly, whether it is AI-based technologies for inspection,
Welcome to Sima Analytics, where innovation meets industry needs. Today, we introduce the UT Maps, a state-of-the-art sensor designed for precise temperature monitoring in reformer tubes. Our sensor is engineered for seamless integration into industrial furnaces, ensuring accurate and reliable temperature readings. Installing the UT Maps is straightforward, and our team ensures smooth integration with your existing furnace setup. Our technicians meticulously calibrate the sensor to meet your specific requirements, ensuring optimal performance right from the start.
But it will not reach most people. It will remain as paper or
once installed, the UT Maps begins transmitting real-time temperature data to your dashboard. The dashboard provides instant updates on temperature trends, allowing you to make informed decisions and maintain operational efficiency.
Of that absolutely would not exist.
Should temperatures approach or exceed the safety threshold, the UT Maps triggers an immediate alert. This alert system ensures swift action, minimizing risks and maximizing productivity in your industrial processes. Experience the power of real-time monitoring with the UT Maps. Contact us today to elevate your industrial operations to new heights.
Lovely, and then it is accepted and works every time. Whenever it's asked to work, it will work. In the lab, it will work only when the person is there, and then he will also have to do some soldering and tinkering to make it work. That is the difference, right? So that, and then of course, understanding the business perspective. Those are issues that, so I'm just going to give you some examples which might be relevant to some of your things. So for instance, Dhwani Research, which is located a few kilometers from here, let me go here. Okay. Okay. This is actually a sonar. It depends on this is the largest ever built, right? And water can be 6 meters, 3 meters by 4 meters. Right? That will be the volume of material. Can be composite, so that is one section of the sonar dome, which covers the sonar under the ship. That is a much more complicated job than that. More importantly, what we are also providing, and nobody else is able to do, is a complete digital twin. So whatever I do in the computer is from reality. But whatever has reality comes back. That is a feature that didn't exist before we introduced it. Now others are doing it. Another example would be this is work that we did with Mazagon Docks initially. Today, everybody like L&Ts and Reliance, all of them are trying to use this, which is weld inspection but completely automated and robotized. Unlike a common situation where you need experts to look at inspection, we are able to get rid of that expertise, make very informed decisions by using automation with using AI, Today, companies like L&T, shipbuilding companies, all of them are now using our weld inspection hardware and software, right? With very limited requirement for the kind of expertise that normally is required. So they can improve productivity, they can improve reliability. Okay. So I'll just continue to go. Another company, Detect Technologies, today is in several, this company alone constitute 50% of the employment that I talked about earlier. We employ about 600 people globally. They look at building intelligence into any manufacturing facility, right? So wherein both compliance and safety are automated using AI. So this just gives you a list of various, models they have, AI models they have that allow them to make places safe and more efficient. Similarly, another company called Maximum Labs contributes towards a very interesting for a shutdown period, an ERP for shutdown, which makes processes more efficient during shutdown. And finally, a company called Zyma Analytics that came out in 2020 looks at creating IoT platform for hostile environment and particularly for marine environment. I want to just say this. This is an example that they now look at providing a complete monitoring of the engine, whether it is the thermal mapping of the engine, whether vibration mapping of the engine, or whether it is the oil quality. Okay, so all of them continuously monitored. So an IoT platform for the engine room for marine is something that they are now offering. They're commercially, it's coming out with a couple of partners, user industry in the marine side. So you can monitor the engine, make sure the engine is efficiently being used. At the same time, it also allows you to not have any reliability issue during actual deployment. So this is something that we are doing efficient, in a very different way. Finally, last story, we just not about engineering also. We are also about social responsibility. So one of our companies is using robotics, but to solve a couple of very important problems. One is the last mile water. Your last mile pipeline is your biggest issue with water. Sometimes you open the water, you get a brown colored water. You don't know what is in it. So we are trying to look and see if we can. So we're now operating with about 15, now it's 15 cities in India. We are trying to make sure that the water pipelines are safer. In fact, just one example, in Hubli, about a year ago, after our intervention, 10,000 homes got clean water the next day. Okay, because we found exactly where the problem was. Similarly, with septic tank cleaning, we are trying to solve the problem that you and I have made happen, which is the fact that you make people go into the septic tank. We are now completely robotized it, and there are quite a few changes we are doing. With that, I'll just stop right now. I know that I don't want to delay this thing, but thank you so much for the opportunity. The message is very simple. We have technologists, we have good researchers, amazing facilities, great ideas, no dearth of talent, no dearth of opportunity. How do we take that? How do you take what you have in your lab and make an impact? So if you guys are really interested, I can bring a team here which can do a 1 day or 2 day or a 3 day program for you guys, okay, which will try to at least address that impact problem. How do you look at your research and say, what can it impact? How can it impact society? How can it impact industry? So this is a program I will be very happy to work with you guys, okay? But we are doing it across the country today, all right? And we'll be very happy to do it here also, all right? Thank you.
Thank you very much, sir, for extending your helping hand. Next, next talk is by I'd like to request our scientist, Mr. M. Sankar sir, to kindly honor the guest with a memento.
Thank you.
Is the serial number?
With this, we move on to the next talk, which is on indigenous development of CTD sensor for ocean observation, which is by Mr. T.S. Rijit of MCON Private Limited, Kochi. CTD sensors are critical for ocean observations, and developing them indigenously is a major milestone. Mr. Sujit from NCOM Private Limited will now take us through the advancements in CTD sensor technology. Welcome.
Minimum. Because of you.
Good morning. So I am Srijit from MCON. We are a company which is running for last 35 years, started by my father. He was an ICR scientist, so I am the second generation. We are into sensor development. That's our core area. We have about 150 different type of sensors for oceanography, agriculture, hydrology, and soil science, mainly. We have received the national award from MSME from Government of India. We have two different activities. One is developing new sensors. So many departments and many industries come to us, discuss their problem, and we give solutions for that. That's how we develop the sensors. And for the last 30 years, we have developed around 150 sensors, which have been used in around 300 universities in the country and many other research institutions. So these are the areas: agricultural science, post-harvest technology, marine science, ocean technology, fish processing, fishing technology, water resource management, dam safety, architectural and structural engineering, hydrodynamic model studies. All our technology is fully indigenous, so we don't have to depend on any other foreign body. So that is our core idea. So when we design something, we understand the location and then we design accordingly. It's not just do something and make sure that it goes into any situation. It won't work like that. For each different type of situation, we have to design, find the range, find the type of product, find the type of material to be used, and a lot of things are there. And most of our products have been tested at FCRI Palakkad, IMD Pune, CWPRS Pune, IIT Chennai, STIC. This I am skipping because it may not be relevant. Yeah. Water conductivity sensor is one of our product which we have been selling for around 20 years. And it is based on conductivity principle. And recently we have developed this for DRDO for their XBT probes, expendable temperature probes, and CTDs also. This is our most simple probe, which somebody can take and dip the sensor to the required water body and take measurements. This is a portable model. This is also some other sensors which are connected to a handheld device, dissolved oxygen, ORP, conductivity, temperature sensor. And this is the one which we have started. We have collaborated with the NPOL, Cochin, DRDO, and we have started selling them. About 2,000 sensors are already been used by Navy, and around 15,000 are in under production for 1 year. So this is like a small ball which will be dropped from the ship, I mean the deck, or from submarines. So when they travel, we are recording in around 20 samples per second, and the entire data comes to the ship through a single wire communication. Now this is another work we have just started. We are just planning to come out with a capacitance-based sensor for measuring conductivity, I mean salinity. So we have done some initial tests and found very good results. There are a lot of further activities to be done, but it is a promising area. Using capacitance, we can directly measure salinity. These are other sensors like sea surface sensor, microwave sensors to measure the oscillatory wave underwater. This was designed for studying chagara. It's a fish formation happening in the coastal sites of Kerala. So that was done for that. Then meteorological sensors for buoy, sensors to measure turbidity, sensors to measure the wave profile in a buoy. Then tide gauges of different models have been used throughout the Indian coastal lines. And I don't have to mention all this. Once you measure, everything is going to the server and you can get it. This is another product which was designed for Adani port. So this is how we come into picture. People come and say that I need to measure this thing. Now this is a typical case. In Adani, when the Adani port was developed, it is a coastal port, you know about it. So a lot of sand is being taken, and during construction, a lot of sediments are again being deposited. And this things happens in a very coastal line where you cannot do a profiling, ultrasonic profiling. So they wanted to know how much soil is being taken away and how much sediments are getting deposited. So we designed a new sensor which can be dragged from the shore, and it gives a very good profile of what's below the water. So the cost is also just 2 to 3 lakh only. These are current meters which will be used by in the ocean, which gives velocity, depth, and direction of current. These are tide gauges, different models. This is another product we recently launched to measure the silt in water. In fact, there is no sensor to measure silt in water as such. So we have been using an inductive sensor which will measure the density. When suspended particles in water creates a change in density, and it's very small. So we have designed a sensor which will take sample, do the measurement, and release it back. So these sensors are used by soil conservation research institutes throughout the country. This is for measuring sediments in rivers or water bodies. This is basically a weighing scale which can be immersed in water. That's all. To be very simple. Thank you.
Thank you very much, sir. That was a highly informative session. If any question from the audience, because sir was kind enough to finish within the timeline, sir.
We do pressure testing. Mainly it will be pressure test for ocean applications. It will be pressure testing and comparing data with some known products. For conductivity, we did test with Seabird as well as RBR. Most of the tests were done in NPOL. So they did the entire pressure test and sea testing. About 10-15 sea trials were conducted.
Is there any validation test you did for your connectivity sensors?
Yeah.
Any graph you have now?
Right now I don't have, but I can share. We have done around 10 to 15 sea trials with Seabird as well as RBR.
You were showing some wind sensors, no?
Yeah. Yeah.
Is it a marine grade or it is for
The one which I showed you is for land application, but we have marine kind of sensors.
Okay. So is it being used now?
Yes, it is being used by PUSAT as well as Andhra University in the Bay of Bengal side. Wind sensor is 30 meter per second. Minimum is 0.02 meter.
Thank you. In the interest of time, we'll move on to the next presentation. I'll request Sri S. Muthukumarvel sir to kindly honor the speaker with a memento in front of the billboard. Please, sir. Moving on to the next talk, it is on development of non-contact CTD sensor. Building on the previous session, we now move on to the non-contact CTD sensor by Professor Bobby George from IIT Madras. He specializes in sensor interface electronics and instrumentation. His work focuses on developing advanced sensor for industrial, biomedical, and oceanographic applications, including water quality and environmental monitoring. A key contributor to ingenious sensor development, he has published extensively in IEEE journals. Thank you very much, sir, for coming here and delivering the talk. Over to you, sir.
Yeah, thank you. Good afternoon. I'm Bobby. I joined IIT Madras 2010. Since then, I got opportunity to work with NIoT on several projects. So I'll present 3 of them briefly. May go a little bit into details, but I will not bore you much. So the last presenter talked about the CTD sensor, and he had mentioned about capacitive sensor. In fact, we were the one first proposed this idea. So we'll go to that soon. Yeah, of course, now I don't need to show this. So CTD means conductivity, temperature, and pressure. And of course, for temperature and pressure, there are sensors available. While in the case of conductivity measurement, there are some challenges still, and existing ones, I mean, like the one bought from Seabird, cost a lot. So the question was, can we somehow develop something new? And then we looked at, of course, this is, I mean, you drop it, sample, and then it comes up. This was discussed already. So we looked at what is already there. I mean, of course, we have this 2 electrodes dipped into water. You can measure, but then there will be contamination over time. the results will be dominated by that. Of course, there is also inductive based method, but the current path is not fixed, so there can be errors. What we looked at is there a way you can measure not by exposing this electrodes to the water? So the solution was something like this. We have a couple of electrodes in a tube. Some of them are exposed to water, but the sensitive electrodes are not, exposed to water. That was the idea. I think that's why he called it as capacitive, because these electrodes are not seeing the water. So as you can see here, this is hiding from the water, so the contamination issue will not be there. But the question is, how will you measure? Of course, I can send a current, apply a voltage and measure this current here. Look at the voltage drop there. But then there will be current going through the water also. This is immersion type. So how do you stop that? I have another electrode in that corner, which is connected to ground. So most of this current will go to ground. So the question is, how will I measure this RX, which is capacitively coupled to these terminals? Right? So this problem is simplified to that. And like he mentioned, it's a capacitive method, but actually you are measuring the resistance or resistivity of that water column. But the water column is coupled in a capacitive way. These capacitance may also vary, so the output should be independent of that. So the overall equivalent circuit can be something like this. This is what I want to measure. These are present. These may be varying. So how will I measure? In the sense, somehow I need to measure from these two terminals without drawing any current. So we came up with an electronic scheme where you inject some current, but then these, this is the electrical equivalent circuit, and these are the two capacitors I mentioned. And these two terminals are available to us. We are automatically adjusting these voltages in a way that this voltage is equal to this voltage. I don't have to, explain how that is achieved now. Once that is done, that means there is no current through this. So at that time, I can just measure these two voltages. I know the voltage across this. I know the current going through this. I know the dimensions. So conductivity can be directly calculated. Let's skip that. So this was the actual idea. So now if you look at the sensitive electrodes are not seeing water. The magnetic mechanism, which is heavy and non-linearity is present, those things are not used in this. So a lot of benefits. Yeah, I have mentioned that already. Now we were a little bit more greedy. I've shown that these electrodes are exposed to water. So in case the water is, corrosive fluid, not just seawater. In that case, these may, we may not see the electrode after some time. In the sense, it may get corroded. So can I avoid them? So what we have done is we have done a marriage between this and this inductive mechanism. So I have used one of those coils to send current through that. And I have used one of the other coil to measure the current through that. So I know the current flowing through that. So basically this mechanism, the coils are not exposed to water. So there is no contamination or other issues there. Only problem was undefined current path. Now in this, I have the defined current path. So this is that mechanism where you use one coil to send current through this, use another one to measure that, and measure the voltage drop here. So you know the current, you know the voltage, the conductivity can be straight away calculated. Of course, it's although it looks very straightforward, it is not that straightforward. We will need a little bit of electronics. Again, I think now you may not be in a mood to look at this. So this is the water column. You are injecting some current. So there is some current going through that. That induces some voltage in this. I get a corresponding output there, which gives the current flowing to the water column. Now, that current induces some voltage, introduces or there is a voltage drop corresponding to that. Now, I can simplify the electrical equivalent circuit like this. It is coupled through two capacitors again. You have another voltage which is in phase with this. So that current will have that information about IW, RW. Oh, sorry. Yeah. Right. Only thing is, the output. I mean, it has the information about RW. At the same time, it's also sensitive to the value of these capacitors. If that change, output will change. So we have made some more improvement where I inject another non-voltage at a different frequency, pass through the same circuit and measure these capacitance values, and then correct for it. So from there, I can actually calculate the value RW just by based on those two measurements. So that way, this is fully non-contact. You are not exposing any electrode, any coil, nothing to water, and it's fully calculable. So that is how we were able to get very good accuracy. These are some of the photographs. These are some of the long-term measurements that we have done in the lab. Later, Srini has taken this into field and then much more experiments. Another 10 minutes or 5 minutes, I will briefly go through some of the other work that I have done with NIoT. I mean, wear and tear, you know, this photograph, it's clear, right? And when it's about to happen, of course, there will be very micron size particles will be coming out. So the hydraulic system healthiness could be assessed based on this information. So somehow if we can measure this particle going through the hydraulic tube, you can assess the healthiness. There are mechanisms already available, but when you have, let's say, thick pipe, right, one of the ways, I mean, if it's a metallic particle and if you have a coil, the inductance of that coil will change. So this mechanism is well known. But when you have, let's say, high pressure tubes, it will be thick. And if you put a coil surrounding that, you may not see anything. So we came up with a mechanism where we have two coils. One is outside, while there is another coil which is inside the tube. But I don't make any electrical connection to that. They are just magnetically coupled. And we have shown that, I mean, I measure from here. These things are in the tube. And we looked at the phase, and the phase has that information because that phase change is quite sensitive. And what we have shown is, I mean, this is the experimental setup. This is the probe that you have developed, which is introduced into the hydraulic line. And we were able to sense up to 75 micron very reliably. You can go up to 30, 35 micron down. That's what the noise level shows. So this was another development which was done by Dr. Muthuvel from here, along with myself and Rambos. Another small work that we have done is, of course, if you want to measure ocean current, there is SPCM, I mean Doppler-based sensors. Let's say this is installed in the buoy, and as you can see, this is also exposed to seawater. There will be biofouling and other issues. Also, it's quite expensive. So we were just brainstorming, is there any other easier way to do this? So as you can see, I mean, if there is a current, this will be get dragged, and then this anchor is the one holding it. So why not just measure the strain on that, right? So we simply introduced a load cell here. In fact, NIoT has done an experiment with load cell for a different purpose to see what's the maximum, or to see what's the stress it experiences, right? So we just use that data, and then from there we found, yeah, this is the setup and things like that. I mean, from where, I mean, in this, the load cell is introduced here, and this is the data that we have used. We have collected data from two data buoys on these two locations. And what we found is, if you look at the correlation between the mooring load and the surface current, I mean, during heavy cyclone and so on, because it's strained, you get very good correlation, right? And that's the time probably the other sensors fail to work. But this one, I mean, unless otherwise the wire is broken, until that, this will be working correctly. So you can see the mooring load data and the actual data. But for low, what shall we say, currents, what happens is, I mean, in the previous diagram, you have seen there is an S curve. So it will not be under strain. Only as the current increases, there will be a strain, and you will be able to measure correctly. So we are working on this to improvise measurement on the lower current regions also. So these are the brief about some of the work that we have done. These are the team members. For example, for conductivity meter, Srini and Tata Sudhakar, Professor Jagdish Kumar, and Tejaswini was a PhD scholar. And Muthuvel, I mean, he was doing his PhD at that time. And Ramdas sir was there for the particle measurement. And now the work on current measurement, we have a team, and Vishwajit is doing his PhD on this topic. Thank you.
Thank you, sir, for an insightful presentation. Any questions by the audience?
Good. I think there are.
On that note, sir will be available. During the lunch, we can have a discussion. On that note, I'd request Mr. Arul Muthaiya, Group Head Ocean Observation System, to kindly honor the guest, to honor the speaker with a memento. Next Monday, Bharti madam. Next speaker is Bharti ma'am. Can I please request you to share your presentation? Thank you very much, Arul sir and Bobby sir. Next, we move on to the next presentation, titled Design and Development of Fiber Optic Sensors for Oceanographic Applications. The speaker is Dr. R. Bharti, Satyabhama Institute of Science and Technology, Chennai. Fiber optic sensors have revolutionized oceanographic data collection. Mr. Bharti from Satyabhama Institute will elaborate on their applications and advantages. Over to Dr. Bharti. Okay. So, next speaker. We can move on to the next. So, in the interest of time, we'll move on to the next speaker. The next speaker, if I am right, just a minute. Yeah, the next speaker is. Yeah, the next speaker is Mrs. Sayantani Lala, senior. No. Mr. Sayantani Lala, senior. She is a senior scientist at CGCRI CSIR. Fiber optic sensors continue to evolve. Mrs. Sayantali Lala from CGCRI will now discuss the latest innovations. Welcome, ma'am. Ma'am, please, you can guide her.
I know.
Can you see my pendrive? Black pendrive. Yeah, ma'am. You can. Is that the presentation? Yeah, thank you. Sorry for the hiccup. We will go ahead with the presentation by Dr. Sayanti. Over to you, ma'am.
Good afternoon, everyone. I am Shayantani Lala. I am working as a senior scientist in Central Glass and Ceramics Research Institute in Kolkata. So basically, I'm working in the fiber optics and photonics division, and we are looking into various applications of fiber optic sensors, mainly fiber bracketting sensors at this moment, but we are venturing into other sensors as well. So I'll be talking about what are the applications of the fiber optic sensors and what are the principle it follows, and we'll delve into that. So after doing comprehensive literature study, so I found that these are the sensors which are needed in ocean, and all conventional sensors or electronic sensors or MEM sensor are in that, where we can see that there are, for the physical sensors, chemical sensors, optical, acoustic and biological sensors, a number of sensors are there. This institute will know a better background to the importance of ocean than me, but I will still say that ocean observation technology is the forerunner for the development for marine science, which is an important symbol for a country's comprehensive national power, among other things. So there are mostly electronic sensors which are used, which has high accuracy and wide predictability, but there are certain challenges also to electronic sensors, like they're more expensive, they're large, sometimes they're large, they are susceptible to electromagnetic interference, which is a major drawback, and they are not applicable for the surface and the micro nanoscale of seawater detection. So coming to that, why we have fiber optic sensors, we can use not to replace the electronic sensors, but in conjunction with the electronic sensors. So some of the shortcomings can be addressed because fiber optic sensors are highly sensitive, they have high temperature resistance, there is an ease of multiplexing, that is, in a single system, single fiber, a number of sensors can be embedded, so the amount of cabling which is involved in sensors is reduced comprehensively. And it's low signal loss in fiber optic cables. One of the major advantages of a fiber optic sensor is the resistance to external electromagnetic interference and its robustness in harsh environment. Because it is a passive sensor, it can give stable measurements over a long period of time. There are different fiber optic sensors. First is the interferometric sensors, which is fiber bracketting sensors, which actually measures how much the light, the distance of the between the light is there, how much the light is there. Mach-Zehnder interferometers and Michelson interferometers. Then we are going for distributed fiber optic sensors, which is distributed temperature sensor, distributed acoustic and strain sensor. So in the interferometric sensors, what we do, they are point sensors. So we have a single sensor and we can have an array of sensors. Whereas in a distributed fiber optic sensor, we have a single fiber optic sensor and the fiber can sense at each and every point. So the whole fiber is a sensor itself. There is intensity-based sensors, spectroscopic-based sensors, and polarimetric sensors, and also hybrid fiber optic systems. We can use one in conjunction with the other to bring out a more comprehensive system. So coming back to the previous chart, with the help of fiber optic sensors, the one in greens, we can develop fiber optic alternatives for the conventional sensors which are available in the market for the other types of conventional type of sensors. This is I'll be going into fiber bracketting sensors. So basically, we are right now, we are into pressure sensors, temperature sensor, and vibration sensors using fiber bracketting technology. So fiber bracketting technology is basically based on Bragg's law. So in a fiber, there is certain amount of I'm not able to find the word. There is certain amount of imperfection is there in a fiber. So the light wave will go through the fiber and some of the wavelength will reflect back. This is called the Bragg's wavelength. Now this reflected wavelength is something which we measure. We are not interested with what is transmitted. Only a narrow part of the wavelength will be reflected, which we will measure. So here we can say that this is the, which one is? There's a pointer, okay. So this one is the incident spectrum. Now when it is going inside the fiber, this is the transmitted one and this is a reflected spectrum. Now this Bragg's law, this wavelength, it is sensitive to strain and temperature. So whenever it is attached to any mother structure, right, there is a parent structure and that structure is strained or there is a temperature change in it, so there will be a shift in the wavelength. and we can actually interrogate this wavelength shift, and we can collaborate it with the amount of strain or the amount of temperature which is there, change is there, and this is how we measure the physical quantities. So there are, how do we introduce the imperfections? This is called the grating writing. So there are two types of facility which are available in CGCRI. One is the femtosecond grating writing system. So we introduce the imperfections with the help of a femtosecond laser with burst of laser at short intervals over a period, short period of the fiber, to introduce the imperfections. And another which we use a phase mask technique, that is we have a mask and we give UV beam, and so that we get a patterned FBG. So these are the two different type of writing systems which are there. I would like to just mention here that we are the only lab in India which have a both type of writing system, like femtosecond. This is wholly assembled in CGCRI, and a UV sensor, UV writing system, which we had bought and which we are currently using for our sensor development. So the next is a distributed optical sensor. So I'll not go into much details of it, only that there are three types. One is the OFDR, second is OTDR, and DAS. So OFDR is based on the frequency of light. So we send different frequency of light into the fiber, and with the interference pattern it creates with a reference laser, we get the change. Pi OTDR is a time domain which we give short pulses of laser through the fiber, and then with the interference pattern which is reflected back, we get this what is the sensor is there. And DAS is it is an acoustic sensing, and we go for acoustic or the sound waves. Here we are not using the light waves but the sound waves, and basically it is used for dynamic sensing, mainly for seismic sensors. So these are some schematic. If anyone is interested, we can discuss. We have developed all this prototype system in lab. The laboratory prototype is there, but we have not yet commercialized it, or we have not utilized it yet with any industry or academic partner. So I'll not go into this detail. There are some recent studies where we can see that a number of fiber optic sensors are coming to all what I have covered till now, that there are many fiber optic sensors which can be used in conjunction with the current electrical sensors. Here you can see there are a lot of sensors. All of these are fiber optic sensors. For example, this is a MZI, Mach-Zehnder interferometer with a fiber Bragg grating sensor, which give a sensitivity of 0.29 nanometer per pH. This is for pH sensors. This is for heavy metal sensors, salinity sensors, and pressure sensors. You can see there are a number of alternatives of fiber optic sensors which can be used. These are all academic studies, and the prototypes can be developed in the lab or customized according to the requirement of the industry or any other academic institution. Another thing which is very interesting, and we are very interested in developing it, is the DAS technology that is used for seismic sensors. So DAS is distributed acoustic sensing, like we have said. So there is a study, and there are studies in US which are going on, that they are using the dark fibers. So in the seabed, for our optical communication, all of you know that there are many fibers in the seabed, right? Some of it are active and some of it are not active. Which are not active, those fibers are called the dark fibers. So what they're using the perturbations for the dark fibers in they are sending sound in it, and with the perturbations they are able to detect the seismicity, the sea floor seismicity with the sensors. So this is something which we are very interested in. And another is, you can see that one more which is very related to marine observations but not directly, is the offshore structures. So fiber optic sensors or the fiber Bragg grating sensors can be used for structural health monitoring of offshore structures, marine structures, and also for ships. Probably, as you know, the most famous ship in the history is the Titanic, which I have heard has, I don't know how much true my knowledge is, but I've heard it has failed due to the material. There were some shortcomings in the material of the steel, right? So it had cracked. So that kind of intervention or that kind of sensing to for the early detection, whether it is some crack is there or not, that can be fiber bracketting sensors can be used for that. But there are obviously some challenges in the fiber optic sensors. Why it is not commercialized till now? First is the growth of microorganisms and algae on cable, but I think that is common for many sensors, and we can work on a more compatible and rugged cable structure for that. There is some kind of signal loss which is there over the long periods, and also providing continuous light source to deep sea sensors is difficult due to the remote nature of deployment, because this is not a wireless sensor. This has a fiber will be the sensing element. It is the sensor and it is the transmitter. So obviously that is what is needed to be done, and how compatible it can be with the current sensors. So here it opens up to another challenge, is the interrogator. So the interrogator, if an optical interrogator, can be made a little more compatible, a little more with the moorings, or little portable, so that it can, and that can be connected to the wireless, that can give wireless signals to the shore. So that is something also a very new research area which can delve into, optical interrogators. Next is, okay, so we have a mission with NIOT, Deep Ocean Mission, and we are working in that. So we had proposed certain sensors like wave sensor, depth sensor, temperature sensor, salinity, tsunami, and air humidity sensors, out of which 4 sensors we are currently working on: wave sensor, depth sensor, temperature sensor, and air humidity sensor. The first 3 are fiber optic sensors, and the last one is the electronic sensor. So this is suppose which we had proposed, right? So this is a fiber optic wave sensors. Basically, it is a vibration triaxial vibration sensor, and we have customized a design. We are proposing that we will customize the design according to the range and the accuracy. It's a 6-dimensional fiber optic FBG accelerometer. Next is the temperature and depth sensor, like everyone is talking, which is a very, very important sensor. And we are providing a fiber optic solution to that. Again, because it is a passive sensor, it has stable movements and it does not have electromagnetic interference. So these are the key points. This is a salinity and conductivity. So here we are using a coating-based sensor. So if the fiber bracketting is sensitive to changes in strain, and also sensitive to change in the refractive index. I will take just 2 minutes more. So because of that, if we change the coating of the sensor in which the fiber is housed, and because of that the refractive index is changed according to the salinity amount. So that is the principle on which this salinity sensor will work. Next is the pressure sensor for tsunami sensor, which we had proposed. Fiber optic pressure sensor, I think one of the areas which NIOT is keen to work. And another is the air humidity sensor, which is already, it's an electronic sensor. Okay, so these are the objectives I have already mentioned. And okay, so the status of the work is that the design of the wave sensor and the temperature sensor is completed. We are going to fabricate it. For the air humidity sensors, it is ready. Again, the fabrication is ready, but it is the stability test in a corrosive environment needs to be done. And other things I'm not going into. So this is the final current status of the sensors, the design. This is the wave sensor. This is the depth sensor, and the air humidity sensor, which is again dependent on the capacitance. Future collaborations is the tsunami sensor, which is basically fiber optic pressure sensors. Moisture sensor, which we can, instead of electronic, we can also have a fiber optic alternative for that. Biosensor, which again works on the, because of the, if we replace the coating, we can have a biosensor, we can work into that. Dissolved gases and seismic sensors, we have already making a hydrogen sensor in the hydrogen mission project. So dissolved gases is something which we have the capability on, we can work on. And seismic sensors, like we had said, for the DAS. In addition to this, there are some things which I wanted to point. We are already, like Sir had said, that there is a vast difference between the prototype and the production. So we are already addressing that. We have an ecosystem with, we have a center of excellence with MIT, that is Ministry of Electronics and IT. So with them, we are making a center of excellence where we will train small scale manufacturer to make certain sensors. For now, the sensors are pressure sensors, tilt sensors, and vibration sensors, but we can obviously extend into it. Second thing is that another thing which NIOT is working is the buoys. So CGCRI, not FOPD, that is not fiber optics division, but CGCR has the capability for ceramic buoys, which can be customized at different length, at different depths. That can be one thing which collaboration can be done. And also, I think that's that. And I hope I could clarify upon or delve upon the future collaborations, I think, which is the objective of this workshop. Thank you very much.
Thank you, ma'am, for highlighting fiber optics for sensors. Any questions? If there are no questions, I request our senior scientist, Mr. Sankar sir, to kindly honor the speaker with a memento. Ma'am, can you please move in front of the banner? So, in the interest of time, I'll give an introduction about the next speaker. The next speaker is Dr. R. Bharti. As he'll be presenting on. Thank you very much, sir and ma'am. The next talk is on design and development of fiber optic sensors for oceanographic application by Dr. R. Bharti from Satyabhama University. Fiber optics have revolutionized oceanographic data collection. Dr. Bharti from Satyabhama Institute will elaborate their application and advantages. Welcome, ma'am.
As a young researcher, it's my pleasure to deliver the talk on fiber optic sensors in front of the professors and other industrialists. As before, ma'am has discussed many things about fiber optics. I just conclude all those things with my presentation. As to the advancement in the optoelectronic devices, fiber optic sensors now are frontier in the field of sensing. As ma'am said, fiber optics, I have just fiber optic sensors are used in many applications. I have just listed out the fiber optics which can be used for the physical, chemical, and biological parameters, that too in situ with oceans. Sure, yes, the basic principle, as we all know, fiber optics, here we are using optical fiber to carry the light signals. The basic idea of fiber optical sensing is to modulate the light properties. For example, by modulating the intensity, phase, or the wavelength of the light, we can measure the parameters to be monitored. So for this, a basic component we need is optical source and the sensor, the detection system. One more beauty of this optical fiber sensor is we can monitor the parameters either in the reflective mode or in the transmitting mode. So by monitoring the reflecting signal or transmitting signal, one can measure the parameters. Here, as ma'am said, you know that optical sensors are immune to electromagnetic interference. It's passive in nature and it's very small size and we can use for remote operation. And we can use optical fiber sensor because of its multiplexing nature. We can use it for wide range of physical and chemical parameters. And it is also possible to make use of a fiber optical sensor as a point sensor or as a distributed sensor. As if you want to measure a range of sensors like temperature, salinity, or any other chemicals, we can make it a sensor in a single fiber. Particularly with the help of FPG, it's very easy when we go for a single configuration. And one more advantage with respect to fiber optical sensor is many configuration we can structure with the fiber optical. Before going into that, as I said, based on the properties which we are changing, either the phase of the light, intensity, or wavelength, we can classify it. Phase modulation, intensity modulation, wavelength modulation. Before going into that, there are basic two types. One is extrinsic and intrinsic. Extrinsic is nothing but fiber optics are just used to carry the sensing signal. Whereas in intrinsic, the sensing itself fabricated inside the fiber. That is the basic difference. I just move on to that. The basic interferometric sensors. Yes, this is based on creating the interference. This is nothing but the basic property of light is whenever the light passing through the air, for instance, whenever the light is passing through the air, it has some refractive index. When it's any other material, for example, a mirror, it has another refractive index. Then the part of the light get reflected and part of the light get transmitted. Because of this interference pattern, by monitoring the interference pattern, we can have an interference fringe. So when we see here, this is one of the pressure sensor designed or proposed for the oceanographic application. Here we have the fiber and one more diaphragm. So we are forming a cavity here. Cavity is nothing but a gap. So whenever the pressure applies, the flexible diaphragm makes a difference in this length. Whenever the light encounters a change in the length, the interference pattern where I have showed, right, blue color, there is shift to orange color. There is a phase shift from the interference light to the change with respect to the phase. That is the basic idea of the interference. And one more thing, the light we are using, the change in wavelength should be in the range of the wavelength of the light we have used. That is the basic idea of interference based sensor. Here is one of the pressure sensor which is mounted on ROV. Here we are having a fiber optic cable over it. At the end we have a pressure sensor, so we can monitor with the help of this. And another one is surface plasma resonance based sensor. These are evidence based sensor which is used mostly for heavy metal detection or to measure the water pollution and all. The basic idea behind this is to make the light to get interact with the metal. Whenever the light get interact with the metal, it excites the cladding mode resonance. And this type of cladding mode waves are more prone to the RA change. Whenever it encounters any RA change, because of the analyte, it interacts. Analytes here, whenever it interacts with water, it gives some pattern of waveform. Whenever it interacts with the oil, it gives some other pattern because of change in water and oil, refractive index. That is a basic main idea of SPR based sensor. These sensors are mostly used for oil contamination with the water and any other heavy metal detection. And this is photonic crystal fiber. This is also by making a change in the optical fiber structure, we can achieve the photonic crystal fiber structure. And move on to fiber rating. As ma'am already said, because of imperfection. What is the imperfection here? Here, imperfection is in terms of RI, the refractive index. Usually we know core and the cladding as core has a uniform refractive index over the length and cladding has some other refractive index over the length. We are going to make a periodic change in the refractive index of the core at some periodicity. This is a major idea behind the fiber Bragg dating. This is sometimes you are called as a filter. It filters only one wavelength and returns. How it filters a particular wavelength? This is because this periodicity, this change should be periodic over the grating length. If it is non-periodic, we can't be able to get the single light at the transmission or reflection end. Whenever we have a periodicity, that too in the range of wavelength we have used, that is a Bragg condition. If I want to use 1550 nanometer, my periodicity should be off of that. By having the particular periodicity, I can get a particular light gets reflected. Here I am getting only one reflected light. And this, as because of thermal expansion and thermal optical property of fiber, the various minute change in the temperature causes the optical fiber to get expanded. Because of this expansion in the fiber, there will be a change in the periodicity. Because of this change in periodicity, my reflected wavelength gets shifted to blue shift. This is a basic or a major idea behind this fiber Bragg rating. And one more beauty of this fiber Bragg rating is it is inherently sensitive to temperature and strain. It doesn't sensitive to any other parameter. But we can make, just a minute. Yes, but we can make array of sensors to make the particular FPG to get prone to other environments. For example, here I am using a polyimide coated FPG which is sensitive to salinity, and I make acrylate coated FPG which is sensitive to temperature. So within a single fiber and with a single source and with single interrogator, I can measure the two parameters. Here I am saying 2 parameter, but we can extend up to 5 to 10 parameters based on the broadband light source we used and the interrogator we employed. Apart from this, one more advantage with respect to FPGs, we can easily hybrid with any other technology. For example, here, this is for humidity sensor. FPG is used for temperature monitoring, but it is not prone to humidity. How can I implement humidity with the same structure? At the end of the fiber, I can implement a 3000 or PAA coating, which is very much prone to moisture. Whenever it absorbs the moisture, it gets expanded. Because of expansion, as I said, the interference pattern gets varied. So I can monitor with the help of reflected wavelength and interference pattern. I can observe the change in temperature and humidity. Yes. The another point is how we can make a multiplexing of here. The last one, I have used temperature, salinity, and pressure. As initially said, there is an FPG which has two set of ratings. One is prone to only temperature. Another one with polyimide coating, I can able to make is used for a salinity. So, with the hygroscopic material. So, with the FPG, I can measure a temperature and salinity. And what about the pressure? At the end of the fiber, the same thing, I am using the silica diaphragm within the capillary tube. One more challenge with respect to fiber optics, that too with FPG, is cross sensitivity. How to avoid the cross sensitivity? Here we are using the silica ferrule, which is totally not response to the outer temperature or salinity, but it can only response to pressure. These are a few in situ trials where array of FPGs are fabricated in a single cable and it is deployed with the help of source and interrogator. We can measure, and this is already ma'am has explained. Yes. This is one more. This is a proposal from my point. We have FPG. As I said, we have only one reflected wavelength. We can monitor by monitoring or tracking the one peak wavelength. This is the tilted FPG. Here, in normal FPG is perpendicular to the axis of the core. Because of this perpendicularity, whenever light enters, it reflected again. It enters again reflected in the same direction. When it is tilted, during the reflection, part of the light get transmitted to the cladding. So I can excite more number of cladding modes. The major idea behind this is because of this cladding mode, this core is response to temperature and strain alone, but it doesn't respond to RA. But this cladding modes are response along with temperature, strain, and RA. One more advantage is how the cladding mode response to temperature and strain differs with the cladding mode's response to temperature and strain. With this way, with the single structure, I can override the cross sensitivity problem. That is a major idea of tilted fiber backlighting. So one more proposal is here with this 2 more minutes, ma'am. With this, with the single coating on TFPG, one can monitor temperature as well as the salinity without any cross sensitivity challenge. That is a major idea of my research work. And this is actually I have done for humidity and temperature. From the point of, by viewing the graph, we can't be able to distinguish how with cladding modes gets differed. But by using the machine learning algorithm, here I am using few regression algorithms. I have trained the regression algorithms with the transmission spectrum I have observed for different temperature and humidity. I keep on training the regression algorithm, and once I have given particular transmission spectrum getting for particular temperature and humidity, it gives the temperature and humidity based on the training. And I have getting the errors of around 0.1 degree Celsius for temperature and 0.1% for humidity. That too we can even make it to better by using better CNN algorithm or deep neural network. I have used just the machine learning algorithm alone. For that itself I can get. This is one more advantage. We can use single coating material. With single fiber structure, we can measure two parameters. And one more point is, this is a regression algorithm flow. And these are just a conclusion of optical structure which I have used. Recently, optical sensors, many research works are carried out on optical sensors, and very few are under in the under sea trial. But many prototypes and many beautiful research works are already done with prototypes. So further continuation of sea trials is obviously the funding to go on. and more practices made. As an institution, we can get only one optical fiber or two with the fundings. But for further experimentation and go on, we need number of FPGs or we need optical fibers to work on with. And that's all. Thank you.
Thank you, Dr. Bharti. Fiber optic technology with AI can be certainly a game changer in underwater sensing. On that note, I request Dr. Tata Sudhakar, our former scientist G, to kindly honor the speaker with a memento. In front of the banner, please. Ma'am, can you please move to that? So, our next, we will take one more talk before we go for the lunch. The next talk will be on latest trends in underwater sensors by Mrs. Bhuvaneshwari. Ma'am is Senior DGM at BEL. Mrs. Bhuvaneshwari from BEL Bangalore will talk us through the recent advancements and their impacts in underwater sensors. Please welcome, ma'am. Welcome. Yes, ma'am.
Next.
Good afternoon, all. I am Bhuvaneshwari, Senior DGM. I am taking care of, earlier I was in the onboard electronic side. Actually, the presentation what you have made till date will be more on specific design as well as some concepts. But our products, here it will be more about our products with the sonar field. So to before start with like a Bell overview on I represent the industry. So sonar systems manufactured in Bell and what all challenges we face as an industrial production agency, the evolutions in sonar technologies, and our what all the quality assurance we follow in our organization. To start with, can you move it? Next. Next.
This one?
No, next. Okay, we are established in 1954. Ours is an R&D driven company with we are spread across 9 units overall India, and we have 2 research labs, one at Bangalore and one at Ghaziabad, and we have a product development and innovation center. Actually, we are some 8,900 odd employees are there, out of which 548 are engineers and 50% of them are working in R&D. So these are the wide products, and we are covering both defense as well as non-defense segments. And these are the new areas of diversification from defense to arms and ammunitions and other software development, unmanned systems, civil aviations, and medical electronics. So now we'll just directly go to the sonar systems. Actually, we started doing projects for Indian Navy from 1970s onwards. Most of our products are from design partner is technology partner is NPOL. So we are in this field from 1970 onwards. So initially we were working for hull-mounted sonars. Both our products include for surface sonars as well as submarine sonars. Now we have ventured into the airborne sonars also. So we started with in 1980s with a project called APSO and Panchendriya. APSO is for hull-mounted sonars. Panchendriya is for the submarine sonars. Then from there we moved on. Like these are the developments both in sensor wise as well as onboard electronics wise. We have improved over the years, and now we are currently working on these type of sonars. Just a brief on that, I'll explain you later. So first thing is the APSO, which we have supplied to Himagiri class of ships. So which had only one sensor, dual frequency. These are all generally surface sonars. We are active sonars because already we are exposed to the world. So generally we go for an active mode where these are projectors are used for these type of sonars. So earlier it was like you can see the number of cabinets because it is more on production. So we go generally focus on the compactness, modularity, as well as the cost effectiveness. So you can see our evolution was with respect to that. So next is was with variable depth dunking sonar, where we had one, we can the fixed array was, we can lower it at a variable depth, as well as some towed array is there was for a passive. So this is another version of this. These all belongs to ship sonar category, where we had two variants, high frequency, because here depending on the class of ship, the space availability and the configuration which Indian Navy wants, based on that, our systems was progressing, as well as the when we went, because there is a change in the obsolescence. So sorry, change in the electronics and the latest trends. Our electronics and cabinets are also were moving. So this is our latest. Means these are our products. Okay. And coming to submarine sonar, actually here we have 5 sensors. Compared to surface sonars, submarine sonar, actually they are the eye of a submarine, because in case of ship, at least you have a radar or some other means of things where you can communicate. But when a submarine is dived, only sonar is these type of sonars. You have an active sonar, passive sonar, underwater telephony, obstacle avoidance sonar, and an intercept sonar. So actually active sonar, generally we don't use active sonar during our normal operation of, because a general purpose of a submarine is to be silent. So this is used only in case of any emergency. A ping is being used to inform our own other ship for rescue. Second one is the passive sonar. This is our main eye of a sonar, because without which submarine cannot navigate inside when it is dived. So next one is underwater telephony. This is the only means of communication which we have between submarine to ship, or ship to ship. Here in this case, it is between submarine to submarine and submarine to ship. And obstacle avoidance sonar, it's a flank array which is meant mainly whenever a submarine comes up. So it has to avoid any, like if there is any ship or a boat which is there above, to see that there is no obstacle there, this sonar is used. And an intercept sonar, because since our main purpose of an submarine is to be silent and then go for an any tactical scenario. So whenever there is any communication or transmission from any other ship around them, so that will be recognized by this intercept sonar. So these are the hardwares which we have moved from, like we started with the 186 processor to now we are going with a QRI keyboard, like a single processor for both the digital processing as well as controller or softwares. Next. So these are the variants of sonar once again. So pictures of this can be seen. This is an intercept transducer, and we have this passive array, and we have this active, it's a planar array. So these are the variety of sensors which we have been manufactured in them. Okay. So if you see, we actually our like we started, it was like a re-engineering of earlier. Our ship and submarines were built at Russia, as well as they were supplying the sonars for us. So since the long lead time for repair and other things was there, it was an attempt made by NPOL and Bell together to re-engineer this Russian MGK 401 submarine sonar. So from there, these are the products names, Wishes and Wishes 1. This is a passive hydrophone, wherein the number of elements was for 504. From there, now we are working on PS array, passive surveillance array, which is 1056, because these are the, as we grow, it is the volume, because it is a main part of our submarine. So here there is no restriction with the number of cells, because the more the number of cells or more the accuracy, it is the safe of our submarines. Then now we are moving ahead with the conformal array and flank array. Now, similarly, this is the obstacle avoidance sonar. This is also again the Russian from the Russian whatever sensor supplied. We have re-engineered. Earlier, we were using a single element. It will be like you don't had a maintenance point of view. The next part was like individual cells, so that you can, if any array gets any cell gets repaired, it can be replaced by just removing those items. So next one is airborne sonar. wherein here like this concept is like your element should be as your frequency is getting lower, your lambda size increases, so your weight of the equipment also increase. But in case of a helicopter or dunking sonar, you have a weight restriction because your life of your helicopter operation time is hardly 1 hour. So within that, with your fuel consumption and other things, this has been you have to go for a low frequency for submarine detection. So we went for a new concept called a bistatic array, where the passive will be like an umbrella, it opens out. So this is one, and it can operate up to 200 meters depth. Next. Next, one more thing is this linear array, because generally there is a restriction when whatever we have seen is an hull mounted sonar is a standard ones which we have used in almost all the class of ship, frigate, destroyers, and other class of ship. But there is a restriction with respect to the what all you have, like XBT, where people are expecting about XBT and CTD. CTD, those are the inputs for our sonar operations. So when we are lowering with respect to and your whatever the sound waves propagation law, the same thing only suits here. Whenever we are positioning a fixed array, so with respect to the, can you shift to the next one? Next, see, these are the various transducer. Next. Okay, this is our production facility. Okay, I'll explain you about the sonar concept in the later slides. So these are the when we develop any product, how we test it inside our factory. So we have a testing facility from a PCB level to the system level. So finally, as a full sonar system is integrated in our factory, and we checked that before with the simulators and other things. We test it. Next. Similarly, these are the transducer manufacturing facilities. Next. So this is a towed array. Towed array facilities, oil filling, vacuum. This is a neutral buoyancy test. Okay, so this we have a facility to check, because since our sonars are operating maximum about 400 meter depth, so we have a facility up to 45 bar. Next. So we have an acoustic tank facility. Next. So this is for testing our acoustic, taking acoustic measurement inside our factory only, because here our numbers are more. Next. So, okay. Now, major challenges. So this is what I wanted to focus here. See, generally in the design of sonar, what is the major challenges faced by a production agency? I just want to explain you. So first one is the medium parameter. Next. So this is the sound profile, wherein from your CTD or XCTD probes, we get the sound profile, the depth thing, and from there we calculate this sonar performance or the sonic ray plot. So wherein you can see a green mark there. These are called as the transmission, like when you inject a signal, how much it can travel inside water. Okay, so if even though a submarine is very close by, if you see a submarine close by in the red mark area, sonar will not detect. That is the characteristics of the medium. So why we need a CTD probe is important is that. So even like most of our channel, we call this as the sonar channel, where you can find that waves. No? So if a submarine is here, this is called as a dark zone. So in this area, even if anything is there, you will not be able to detect a target. So to find out whether it is an actual target or for this, so you need a like what you call like these plot is very important for us. That is one reason. And next one is like this plot is with reference that your sensor is fixed here. So this plot varies if you are lowering your sensors. Okay, so that only we are going for a various type of sensors. Like when you go with a very high, heavy, like if you are taking a 1 kilohertz or 1.2 kilohertz sensor for lowering it inside a water, and that dragging force and other things, you can never achieve a very low frequency with a transducer of conventional type. So that is why we go with a variety of sensors, like whatever I showed you, like the towed array, and then the helicopter which can go below some 200 kilometers depth, so that your channel, you can shift your sonar channel in a different places so that you can detect that. And this is very important because out of if you say Indian Navy, sonar plays a major role, and it is categorized under a weapon equipment. Okay, it is not, though it is a sensor, it is considered as a weapon equipment, and this plays a very serious role as far as any strategic platform is concerned. Okay, so means you are how much you are able to detect a submarine or a torpedo much before it is being fired from that place. That is the thing which is required by an Indian Navy for their quick reactions in that scenario. Okay, so next. So there are so many problems because like you are like air. Oh, sorry. No, so like air, you cannot. Water is a tough medium. So to understand all these things, more than the sensor, these all things these all parameters plays a heavy role in our design of a sonar. Next. So these are the constraints as far as platform is concerned, because you cannot carry, if you want a 1 kilohertz transducer, the size of your array will be somewhere around 4 to 5 meters. So such a heavy item you cannot carry in a ship. Okay, so how we design different varieties. So these are the things. Okay, the shortage of time. Next. So next year. So these are some of the constraints which we have. And see, from hull mounted sonar, from conventional array, now we are moving towards like mine detection and torpedo detection in active mode. This is a new which we are focusing. Second, towed array, from single line to torpedo. Sorry, next. Okay, these are the improvements which we are planning for in the course of time. Next. Okay. So these are some products which we are currently working. Side scan sonar and navigational sensor, mainly echo sounders, DVL. Next. So this is a diver detection sonar, and most of them we are working with NPOL. Next. So these are other one underwater target training targets. Sub-bottom profiler, this we are working with NIOT. Next one is the turtle level sensor. This is another one. This is a quality assurance plan which we which we generally followed, because it is not, you cannot aim for quality at the end of the product. It should be starting from the start of the project. So what all steps we follow when we take up any new projects, starting from the design phase till its product support, the variety of things have been followed. You can I'll give my presentation, you can just go through it. Next. So these are the, like in hardware design, software design. Next. Design validation.
10 minutes.
Thank you.
Thank you very much, ma'am, for your insightful presentation on sonar. May I request Professor Manal Jakaria, international technical expert in blue economy France, to kindly felicitate the speaker with a memento. Thank you very much, sir and ma'am. Now, before we proceed to the next set of talks, we will take a short break for lunch. Please rejoin at 2:15 for the next session. The lunch is at ground floor in Manthan Hall.